let's move quickly on to databases and data storage. So kind of, we discussed a little bit of this on Monday, kind of broader view from a 40,000 feet aerial view. Today, we'll try to understand databases a little bit closer and also see, why, you, even in GIS, you use relational databases. All relational databases are supported in the GIS systems. And so it's useful to understand what a relational DBMS is and how it does. Data storage is another thing where, because we deal with a number of data repositories, different file formats, so that is also important to understand the implications of that. Any questions so far? Okay. So just to recap what I said on Monday. So we went over a bunch of things. So we went over, file-based data storage and management. What does that imply? We'll study a little bit more. Today we will focus more on the DBMS, not on the others. And if time permits, we will try to cover NoSQL. Okay, so we'll be briefly understand data storage, DBMS, GS, and ArcGIS, and this one highlighted in blue. So, as we said, basic abstraction for storing anything is a file. And it has not changed. All types of file are stored, all your shape files and image files and map files. So who decides how to store things? I mean, so the user or the community decides how it should be stored, because that is going to be extremely important. If you don't store it in a format that is uniformly agreed upon, then you run into a lot of problems in application development. So that's why you have all these file extensions for different types of shaped files, for example. So based on the extension, you know what is the format inside that and how to interpret it and how to use it in a particular application. So typically in a file, you store things as records, fields, and values for structured data. Applications have to be aware of the format. This is very important. It doesn't matter which application it is. They need to know what the format is before they can process and make sense of it. So here is a very simple way to understand what a record format looks like. So you can think everything you store as records. So a file may have 1 million records or 10 million records, and each record may be 4 fields, 5 fields, or 10 fields. If you think of just an employee information, there may be 5 or 6 fields, and they have to be stored on the disk in a file, which is stored on the disk. And then this is what you get when you read it. You get this information to the memory, and then you have to use that information. So information about the field types is the same for all the records in a file, and this is typically stored in system catalog. So you can think of system catalogs as one kind of metadata that is used inside a DBMS to interpret or understand what a file format is, how it looks, or what a table is, what are the contents of the table. So data, metadata is used everywhere, but maybe in slightly different ways. So when you come to file-based applications, as we said, the application has to read the record at a time or a block at a time, and then interpret the fields and then take action. So understanding the representation is key to the application. So application is very tightly integrated with the representation format. It doesn't matter. .csv file makes it easier to separate them using a split in Python on a comma, if it's a comma separated file, or a white space, if it is a tab separated file. So you can do that easily, but you still have to know the representation of the format. Makes it difficult to change the format. So this dependency, this tight control between, or tight coupling between the file representation and application makes it very difficult to change the file format once designed. Revision or enhancement is difficult. That is why in a lot of different types of files you have, the format has to be adhered to. If the format is changed or extended, you have to change all applications. So this is the biggest software engineering or software development problem. If there are 10 applications using that file, if you change the file format, all 10 applications have to go and revise their code to understand the new format and other requirements. So very rarely you want to do that. Application management is difficult, labor intensive, and prone to errors. Strong coupling or dependency makes this difficult. So difficult to manage duplication and maintain. So if data is spread over many files and the same information, as we saw in the example that I showed you, is present in many, you have to make sure it is represented correctly without inconsistency and managed properly, which is very difficult. So the question is, what is the answer? So here is an example that I want to give you because I was part of this process. So we were doing payroll processing, for example, in the 70s using file-based data. We had to use multiple files because personal information was in one file, wages and other information, hours worked and information was in a different file. So all these files had to be processed together in order to generate pay stubs. And not only that, we had to create a new file, updated file at the end of the process to do it for the next time. On top of that, we were also using tape drives, which I briefly mentioned at that time, as the capacity of the disks were very small. So we had to update these files as well and write what we called a new master if our computation was successful. This process would take at least a day, and maintaining the files for the next one was critical. If there was any kind of error and we had to abort it, then we had to go to the backup file and then restart the whole process till the process is completed. So this is a very difficult process. So this is one of the reasons why we have all the things we have, DBMSs, standards, metadata, and other things to avoid or mitigate this as much as we can. There are additional critical issues that are also not properly handled by the file-based storage. They are, as I said, managing duplicate information. And when you have duplicate information, consistency is a big issue. So if you have student information, duplicated in multiple places, if you don't change address in one file, you have to make sure the address is also changed in the other file. Otherwise, you have two addresses for the same person or two phone numbers for the same person, which causes problems. Concurrent usage, this is a very important thing. If hundreds of users, thousands of users are going to use a particular system, file-based applications are not geared up to handle that. You cannot have the same file open from multiple users and be reading at different places and doing different things. That's a big difficulty with file-based system. Determining how to combine data is another issue. Recovery is another issue in the presence of failure. So it is possible that power failure happens or some other kind of programming failure happens. You might have encountered, like, Windows, when there is a failure, you lose all the information that you were doing, editing and other things, and you have to go back and start with your laptop. This is unacceptable for mission critical applications. And also you cannot query, you can only run applications of query data across files. So needs a new application for each query, and managing large amounts of data is difficult. So there were a bunch of issues that were not properly handled by file representation. So what is a data repository? You can think of a file as part of a data repository. A data repository is a storage space for researchers to deposit data sets associated with it. So it can be one file or a bunch of files that have some relationship between them so that they can be used together, and multiple data sets. So we have already seen earlier a data warehouse as a mechanism for aggregating data from multiple sources and creating a single view of the database. We also heard about data lakes, data marts. Git and GitHub can also be seen as repositories for data. So most of you are familiar with GitHub. This is mainly used not only for data, but also for code, mainly used for code. Data can also be there. Description and documentation can all be there. So many times this is done at the individual or organization level, can also be done broader, is organized, and versions can be maintained, and various all kinds of checks and balances that can be implemented to make sure what is stored in the Git is correct. So I just put this because even if I don't know about these data sources, you guys are very familiar with these sources. These are all repositories for your domain or area. There are a number of them, very large, natural earth data, US Earth Explorer, so on and so forth. So you may be already using and accessing some of these repositories, and you might also look at some of the metadata associated with these repositories. We'll come to some of those issues later. So how do we overcome the problems that we mentioned earlier? So all problems associated with file development can be overcome with the introduction of a database management system. That was the whole purpose with which it came about. By decoupling the data representation from application. This is the key. If the application software does not have to know the data representation, then there is no dependency. You can change your data, or you can change your application software without having to worry about that. But in order to do that, so this is a very commonly used practice in computer science. So we call it kind of a one level of indirection, which means that there is a price to pay, but life is made very difficult, very easy. So this requires data model to represent the application at a higher level of abstraction. So this is the key, is to have an abstraction that can be mapped to a representation, and it can be done by the software. So that's easy to understand and perform computation, the data model. So data model has to be simple and easy. If it is very complicated, then it poses its own problems. You may end up having different levels of abstractions for different purposes. So the bottom line is this requires software that can hide the physical representation of the data model or the abstraction. So one way to understand it easily is think of a compiler. You write your program in Python, but computers don't understand Python, so it has to be converted into a machine language and assembly code in between. And that is done by a compiler. So this compiler is what we call the middleware that takes you from a higher level of abstraction of expressing things in in if-then statements and objects and functions to machine executable code. So that is one form of abstraction that you use. You can think of each language as a different kind of abstraction meant for a different purpose. Think of a web GUI that allows you to access by filling boxes instead of writing a query. That's another kind of abstraction where you interact with drop-down menus and boxes rather than writing a query. But somebody translates that, some software translates that into an executable query behind the scenes. So this is very different from how we were using computers before, using command prompt style and writing commands. So DBMSs can be understood in two different ways, from an end user's perspective and from a system perspective. So here we are only interested in you understanding DBMS as an end user, which means that you may want to understand why DBMSs are needed, for which kind of applications it is used. How do you go from an application requirement to DBMS design? What models are used? We will focus on the relational model. How do you query? You don't have to write an application, but you still have to express queries in a standard language called SQL, and that's easier. How to use a DBMS, whether it is a traditional DBMS like Oracle or a GIS DBMS that we normally use. We won't worry about systems perspective, which is more about how do you implement a DBMS and what are the issues. So need for data models. So additional requirements we listed earlier were derived from enterprise applications. So this is how the need for DBMSs and the banking applications, airline reservation, employee data management, managing inventory. So why were these applications important? Because they had very stringent requirements. So if you take banking, for example, when you deposit an amount into your account, you want to make sure it happens. And if you get a receipt, that amount is added to your account. You don't want the bank coming back and saying, hey, my software failed in between, so your account does not have the proper balance. That is not acceptable. Same thing is true for airline reservations. You reserve an airline seat, it cannot come back and say, sorry, because of some failure, we could not do that. So these were very important critical requirements, like MyMav is another example. So these were not guaranteed by file-based systems or any system. When even today, operating systems do not guarantee this. When an operating system fails, you lose all the work that you have done up to that point unless you save it yourself. But this manually saving is the problem that cannot be used by these applications. It has to be automated. It has to work perfectly. So this is the main thing. So there are a lot of mission critical applications. DBMSs are used, nuclear power plant control and various other things, and they have very stringent requirements for this. So earlier files were created manually without any principled process and only based on the knowledge of the application by the developer, how many files, their contents, formats. So this was a very ad hoc process, to say the least. So think of ad hoc design that could not be carried over to mission critical systems or enterprise applications. So that is the whole motivation for data models. A new approach was needed for taking care of the complex requirements, and you'll see that not only in operating systems, in GIS systems as well. First, applications had to be modeled in a systematic way to make sure data is captured completely, along with interrelationships among data. Functionality on the data should also be captured. What you want to do with the data when you capture the data. Data models were born. So we had hierarchical data model, which led to the development of hierarchical DBMS network model. And finally, the relations led to the development of relational DBMSs. Today, this is the most widely used DBMS. We'll see why. So widely used today, RGS supports all commercial relational DBMSs, and there are others as well. So just briefly, you need to understand what kind of things were used for modeling. The need and the goal was to model real world applications. So even if you take GIS, you are going from a real world application need for putting some information on the map. That is the real world application. You may have map information separately. You may have the data that you want to put on it separately, but the application is to integrate them and view them in some way, and that has to be modeled in some way. So what we call extended entity relationship model was developed in 1970 to capture entities. This was a very simple yet powerful model. A popular model is still being used today for the design of relational DBMSs and others. Many tools are available for this. Real-world objects are expressed as entities, and their relationships are captured using the model. This model is converted automatically algorithmically into relations, hierarchies, or networks. So that is the advantage. So if you can express, still doing the ER model is done by humans, but converting them into relations is done using an algorithm. So here is just an example of a ER diagram for a company founder. So if you are, so here is a person as an entity, and there are different relationships. A sibling of a person is a person. A person is married to another person. A person studies at a university. University is located in a city. A company is located in a city, and a person founded a company. So this is the model, which is easy to understand and interpret. And using this, from this model, you can generate hierarchical network or relational schema, as we call it, in order to implement that. Now, we have been using this. We'll see UML is used in your GIS applications on other programs. So what is not captured in the database or the model is the actions. There is no way to capture actions in a database or in a file because actions are typically done through applications, through interactions. So here is a good example. We all log into various systems. It is done through an application, but a number of data elements are required with additional constraints for doing that, such as username, password, CAPTCHA. So also a password need to be changed. So what is captured in the previous model I showed you is the pieces of data, not the action. The action has to be implemented as an application. So the same thing is true in all your databases. You essentially capture the data. So whether it's a line or a polygon or whatever it is, it's a piece of data. Manifestation of that into a visually understandable thing is done by the software or the application that renders it. Here is another example. I'll skip that. So in addition to modeling data, you also want to query this database for various things. So these are the things like you want to know which book is borrowed by who in a library database. You want to generate report of customers who have not paid the last credit card bill or last two credit card bills. You may want to track a UPS shipment to know the current status. 10 most popular movies generate honor students in the College of Engineering. So this is what you want to do and make sure the data you have captured can provide these answers to these queries. Otherwise, your data capture is incomplete. The second model that is widely used today is what is known as the UML, Unified Modeling Language, based on ER. This is an object management group industry standard. It has support for a lot of things because it's used in large software system development for building a GIS and object-oriented GIS data model and system architecture using UML can be used. Notion of abstract classes are there. It's also there in Java and Python. For example, you can export workspace XML from UML model. You can import into a GDB. You can use UML poster diagrams for generating that script. So UML is widely used today. Here is an example of a UML language class diagram to urban land information system that I found. I may not be able to understand it completely, but you guys will be able to understand it better. So this is how, instead of the ER model, this is the UML model that is used, which goes a little bit farther in representing interactions and behavior and use cases and other things that can be implemented into a system. So is World Wide Web a DBMS? So sometimes this is the question. You have fairly sophisticated search. There is a crawler that indexes the pages. You can do keyword-based search, but currently you cannot, the data is mostly unstructured and typed. You can only search, you cannot modify data. You can't get summaries, complex combinations of data. So actually what it is you have a DBMS behind a web. In some cases, it may be something different. Google, for example, uses other systems in addition to DBMSs. Few guarantees are provided for freshness of data, consistency, fault tolerance. So a lot of critical requirements of a DBMS are missing from the World Wide Web, which may be present in web. Is a file system a DBMS? I'll skip this. You can see that in the interest of time. So let's go to the relational model. What is a relational model that is widely used today? This is a data model, and data model is nothing but a set of concepts and operations on those concepts. Luckily, in the relational model, there's only one concept, the notion of a set. That's one of the reasons why it's easy to understand, and a bunch of operations that we clearly understand. It also has a good mathematical foundation from set theory. So this is the widely used model today based upon the mathematical concept, can be altered. So the important thing is this can be a relation or a set can be viewed as a table with rows and columns, making it easier for a common man to understand without having to understand the mathematics behind it. Can be seen as a spreadsheet, although spreadsheet came much later. So here is an example of a relation. So you can think of it as a table with rows and columns. So here is a student ID, name, login, age, and GPA. So this is also known as this schema, that the first header is known as the schema that describes the attributes, or these are the fields. When this information is stored in a file, these are the fields and this is a record, something like that. The actual values themselves, data, is known as the extension, which has to be populated based on the schema. Why is relational DB found? Because there is an easy to use query language called SQL, structured query language. You can access data without having to learn operators and semantics, without having to write a query in the traditional sense or a program in the traditional sense. This is a very powerful associative query language. Programming understand data storage formats not required. It has a very powerful optimizer that lets you write not a good query, but the system optimizes it behind the scenes. Data and metadata are represented using the same model, relational model, and can be queried. That's one advantage. Very importantly, supports multiple users, recovery from failures and consistency. These are the very important elements. In SQL, you can write queries for expressing things like list female students in the College of Engineering whose cumulative GPA is greater than 3.2. Now, this can be relatively easily translated into a school query without having to write a program. List all students in the CS department in 2022 who got A from every course they took under instructor B. This may look like a complex query, but a complex thing to retrieve, but you can do that. And the good thing is the algorithm for retrieving is how you want. Generate a report listing average salary faculty in each department in the College of Engineering. So if you have to do this, some of this may involve multiple files or multiple relations. Your application has to figure out how to combine them. So DBMS does all of them for you behind the scenes. Of course, these need to be converted into SQL, but that's much easier. Burden of efficient retrieval is on the DBMS, not on the end user. So as I said, there may be multiple levels of abstraction. At least in the DBMS world, we have two levels, physical schema and conceptual schema. The set view comes at the conceptual schema level. Physical schema is how the information is represented, and both are shielded from the user view. So the user does not have to know. The user only has to understand the conceptual view, and the rest is transparent to the user, making it much easier to deal with different types of data, different kinds of data. So you can also think of data exchange formats that we will discuss as schema. So schema is just a way to express the intent, what you want to represent, not the content. So intent versus content. So we have seen this already. A DBMS is an integrated collection of data. That's the key. And it should model a real world enterprise. So we use entities and relationships. A DBMS is nothing but a piece of software. You can think of it as the middleware that is sitting between you and the actual data that is stored on the disk. And it is managing everything that you ask to the DBMS and retrieves and gives you that information. This is also true for GIS. In GIS, you're doing higher level applications and you're not worried about how many files are used underneath, whether in order to do this, you have to access a relational database plus some other kinds of files that hold spatial information, whether it's a vector kind of information. So these are the advantages for using a DBMS. Data independence, very important. Efficiency, data integrity, uniform data administration, very importantly, concurrent access, recovery from crashes, any kind of crash. It can be a power failure, it can be an operating system failure, it can be a program error, it can be a disk crash. It provides persistence, scalability, and portability. This is also important because you want this data to be available for a long periods of time. So you do processing only in memory. So you bring the relevant data for processing in memory, but at the end of the day, the data is stored after all the changes and manipulations in the disk, which is available for the next session. You can also provide a bunch of access control and privacy and other issues. So that is one of the major reasons for doing this. So a relational DBMS needs a schema. A schema is a description of a table. And as I said, this is also a conceptual schema. So here is an example of a table and sort of the schema for this table. So when you first express, you express the schema, which says, here is a table whose name is student, SID has character type of 20 characters, name, age is an integer, GPA is a real number. This gives you the schema. You can also think of it as a metadata, but the actual values have to be populated into the DBMS at different points in time, multiple. So, this database is changing every semester. New students are coming in. Some students are graduating. So there's a constant change to the database, and it keeps the current instances to do the computation that we need to do. So the kind of data types that are supported may be limited. Like, for example, it doesn't support spatial data types, but you can represent it in some other format, either as a file or as a relation, and then write an application for that. Text and numeric data types, date time format, not geared for storing uh, large files. Typically, the way this is done is to put a handle to these images or other files and store the path or the handle so that you can access it, because a lot of these things are rarely updated, but they are accessed or retrieved. Lacks general search capability, meaning if you do not have Google-like search. They allow what we call blobs or binary large objects. SQL can be embedded in many programming languages. There are a number of commercial DBMSs which you might be familiar with. Oracle has the largest market share. Sorry, DB2 is from IBM. SQL Server is from Microsoft. Sybase has a smaller market share that's still there. Some of that have been acquired by SAP. There are some publicly available DBMSs like MySQL, Postgres is used from the literature. I see GIS uses some support Postgres database more than MySQL. So our DBMSs were optimized and used for management of data over a long period of time. This is important. Generating reports, different kinds of analysis. High concurrency, meaning number of users can be very large and it can support them. Guaranteed recovery, we call it ACID property, but this is a very important requirement for a lot of mission critical applications. There are some limitations. Partitioning, for example, is not automatic partitioning of data. Query processing need redesign for taking advantage of partitioning. There were distributed databases that make it available due to distributed connect. So there were a lot of work beyond the simple RDBMS that went on. So this is what we call vertical and horizontal scaling. Vertical scaling is for increasing the amount of CPUs that you use to provide more juice. Horizontal scaling is adding more data capability, adding more disks. Both of them are a little bit difficult for RDMS to scale. That's why you don't see RDMSs on hundreds of processors, unlike MapReduce and other distributed partitioning and processing scales where you can scale to hundreds and thousands of processors. So to summarize the relational model, it's a tabular representation of data. I think the reason why it is popular and widely used, it is very simple and intuitive. You can support integrity constraints. This is another thing that is important because, once you put in inconsistent or incorrect information into database, it stays forever. And it's very difficult to check that because all your subsequent computations and other things are based upon that information. So it's very important. So data entry, we call it data entry is a tough job, and DBMS has some built-in tools to check and make sure the data is consistent and follows certain organizational or other integrity constraints. You cannot do everything in an automated manner, but this is an important area. Powerful and easy to use query language can scale. Tons of utilities are available on that. A lot of object-oriented features have been incorporated into relational DBMS. So there was a big push for ODBMS that didn't happen. Still, there are a few commercial systems that are being used. Other DBMSs, SQL-based, have come about for various purposes, and one of them is the notion of column format DBMSs. So Vertica is one example. This stores data in column format, unlike a relational database which stores data in a row format. Each record is a row of a table, and records are stored, whereas here each column is stored separately, and that has certain advantages for processing and certain kinds of computations. Data encoding and compression can be done better with column representation. What I have seen is that this representation can support some geospatial analytics. I'm not sure how widely it is used by the main experts. I'm not sure. Easily load and export shape files. You can perform spatial joins, as they call it, to see whether two objects intersect and get the answer. Another similar one is the Sybase IQ. Now it's part of SAP. This is also a column-based petabyte scale relational DBMS. There are other column-oriented DBMSs we see, Apache, HBase, MongoDB, MariaDB. So the reason to go for column-oriented, even though it provides good compression, is not just to save storage. Saving storage is important, but more important is when the amount of storage is less, the amount of I/O input output that you have to do is also less. That is the higher cost. That is the kind of the Achilles heel for DBMSs, staging data from disk to main memory and back. And that is still not as advanced as the CPU. The Moore's law does not apply to disk I/O bandwidth, for example, and that is a serious limitation. So I have put together a few slides. I'm not sure whether it captures everything that you need to know. You may know more than this, but this is sort of looking from a computer science person who is interested in the database aspects of any system. So it's a geographic information system is a multi-component environment used to create, manage, visualize, and analyze data and its spatial counterpart. So certainly it has a lot more data in addition to tabular data. So all the spatial data is not stored in the relational format because it's very inefficient to do processing unless you use special ways of doing it. Most data sets can be assigned a spatial location. So the question is, does your data necessarily need to be analyzed in a GIS environment? And the answer, it depends on how you want to understand. So here is an example I got, which seems to, at least for me, indicates, suppose say you have this data, countries and number of conflicts. And so this is a piece of data that is not spatial in any way. And you want to identify top 4 countries with highest conflicts. So that's very easy to do. You can sort on the conflict row or conflict column. You can put it into a relational DBMS, sort on a conflict row, and get that information. So that's easy to do. You don't need anything more. But suppose say you want to find whether the high conflict countries are geographically clustered. So this is a different query or different thing that you want to understand, and that cannot be done by a relational DBMS. So if you want to do that, then you have to have the map of the countries and the way to understand a country name to the map associated with the country name in whatever way you want to do it. And here is one way to do that. So here is a place where the low and dark shadings indicate the level of conflict, and the map feature clearly shows the juxtaposition of countries with different conflict values. And from this, you can immediately answer whether these countries are geographically clustered or not. So to me, this is the difference between what a relational DBMS can do versus what a GIS DBMS is capable of doing with additional information stored in a way that can be combined with the relational information. So that's what happens. You have a lot of data that are still in the numeric or the relational form, but you also have spatial data in different ways. Now you have to integrate them or put them together in a meaningful way to make some sense of it. So this is, to me, is the power of GIS. This is a very simple example, but you can take it to different levels. So a more complex data storage mechanism is required. This is the core of the GIS environment, a spatial database that facilitate the storage and retrieval of data, that define the spatial boundaries, lines or points of entities. This may seem trivial, but without a spatial database, no spatial data exploration would be possible. To me, this is the sort of the quintessential feature of a GIS to going from a, so you can sort of see the previous one as histograms or tab visualization, but those visualizations are different from spatial visualization. So what is GIS? Here are two definitions that I took from USGS and from SC, which is one of the leading vendor of GIS. In the strictest sense, a GIS is a computer system capable of assembling, storing, manipulating, and displaying geographically referenced information, data identified according to their locations. Practitioners also regard the GIS as including operating personnel. SC says geography is a computer-based tool for mapping and analyzing things that exist and events that happen on Earth. GIS technology integrates common database operations such as query and statistical analysis with the unique visual aid. So this is the kind of the summary of what a GIS is. So GIS software, many GIS software applications are available as far as I can see. Some commercial, some open source. Two popular ones seems to be ArcGIS, which is commercial, and QGIS, which is open source. Is it developed? So history has been around for a long time. So it provides a lot of different components, ArcMap, ArcCatchwall, and other things. It's only available for Windows. It can be used on Mac using virtualization tools. I think lately it might be available on Linux as well. I'm not sure. QGIS is a open source software, and I'm not sure. I believe ArcGIS is widely used in education, and we are using it for this tutorial for sure. But if someone wants to play with it, there may be a light version of ArcGIS that's available, plus this may be available for you. So to me, what is the difference of GIS from a traditional DBMS. Two things. One is the software applications that support on top of that, plus the data itself. So different software packages are important for GIS. Central to this is the GIS application package. Just for essential for creating, editing, and using spatial intelligence. So traditional DBMS is only supported for kind of a traditional data types like numeric data, which are not meant to be visualized spatially. Therefore, these packages contain a myriad of GIS functions inherently. Extensions or add-ons or software that extends the capabilities. So extensibility is an important thing. Irrespective of how many tools are there, someone wants to extend it in some way for a particular need or a particular purpose, and that should be possible. Component-based software is the opposite of application software because kind of these software are developed and available. To me, these are similar to the Python packages that you use. So the larger the availability of these packages, the better it is, right? When you can use it, you don't have to understand how to use it, not how to write these packages. So you don't want to understand how pandas is implemented, but you need to understand how it can be used for environment analysis. Utilities are standalone programs that perform a specific function. For example, a file format utility that converts from one type of GIS file to another. So again, this can be easily made available. There are also utilities for traditional DBMS, for example, to split a relation into a CSV file or a tab file or some other kind of file. There are also WebGIS software that helps. So GeoBit database is the terminology that I see constantly with respect to GIS systems. And geodatabase seems to be a collection of files plus relational database systems as a single thing called a geodatabase. So it has collection of geographic data sets plus ability to access and store relational data in any one of the databases available like IBM, DB2, Microsoft Server, or Postgres is a public level. Data seems to be at the core of GIS, and in addition to the relational format, you have vector data and raster data coupled with what is known as the attribute data or metadata. So these things we are more familiar than I can explain. But so metadata, we'll come to that, contains such information as the coordinate system, when the data was created, when it was last updated, who created it, and how to contact them, and definitions for any code. To summarize, I'm going to summarize this and stop it. As I said, we won't get to NoSQL, but that is not very critical because they are new, their usage is not as much. So ArcGIS Desktop consists of several integrated applications. You might be familiar with most of them. ArcCatalog is the data management application used to browse. So for data sets and data files of this last quantity, you have to have a good way to locate them or search them or browse them. A number of software extensions can be added, including 3D analysis, spatial data analysis, and other things. From the end user perspective, ArcGIS has very wide-ranging functionality package up to a generic set of menu-driven applications and workflow. So the next thing was so since we are reaching 10:30, I'm going to stop here and just
Someone had a question in the chat too, asking about the unified modeling language.
okay. So let me put the chat. Okay, does human model actions in a database? So UML is certainly capable of, because UML is meant more for modeling an implementation in a programming language, not just data. So it captures behavior and interactions and use cases so that they can be implemented in the same way in the programming language. Earlier, it was very widely used for Java implementations, but it is application independent and language independent. It can be used for any. Yes, you can do that. So to summarize, in addition to the databases discussed, there are several other types. Just for completeness, main memory databases, string databases, spatial representation. There has been a lot of work going on. Databases also support what we call ACID properties, support concurrent users. Indexing that we did not get into is very important. It perhaps it's used a lot in your case. Mirroring and hot standbys are used for mission critical applications, and that's very, very important and very critical for some of the applications. So with that, I'm going to stop here.